Welcome to this NPTEL lecture on techniques and principles of modern radar system. We were discussing various types of radar. In previous few lectures, we have seen in detail the CW radar. Today, we will see the pulse radar. Now, the pulse radar means instead of sending the transmitted signal continuously, we will have a pulse radar. So, first I will draw a very simple block diagram and then we will see the actual block diagrams that are used. So, first is there will be a pulse modulator, then that if the pulse is not of high power, you require a power amplifier, then that will be given, but we already know that in pulse radar generally the same antenna is used for transmission and reception. We have discussed that antenna is a costly device at RF level, this high microwave level, and since pulse radar is not always transmitting and when it is not transmitting it is listening. So, the same transmitter can be used. So, for that we need a duplexer and that is connected to the antenna. Now, when the transmission is off, the receiving antenna, this same antenna is then receiving, and so duplexer has another path by which the received signal comes to the receiver, and from there is a Doppler filter and we get the velocity of the target, also the range. So, actually instead of Doppler filter I could say the processor, various processor. So, this is a simplified diagram, simplified pulse radar. Now, the first question that comes to our mind if we look at this block diagram, that we know CW production is easier. So, I could have instead of this pulse modulator, I could have kept a CW modulator. Let us say that if I could keep a CW modulator, a CW transmitter, it will produce RF continuous waves and then I will simply make it on and off and that I will give here. So, instead of this, if I do this, can it work as a pulse radar? A CW radar, then on and off. So, for the pulse on time I will make it on, then there will be a switch that will make it off, then the receiver will listen, etc. The question is no, because something is missing in this simplified diagram. Actually, to have this measurement, receiver actually it in a pulse radar also requires a very important connection, that whatever is getting transmitted it should have that in the receiver, so that it can compare what is happening, because we know that the measurement requires the thing also Doppler, that will require that what is the transmitted frequency and compared to that how much shift is there. So, there is a connection required. So, due to this part actually this scheme won't work. So, this was the correct scheme, that there should be a pulse modulator, because if I do it with CW that on off. So, during off time the problem will be that the receiver won't get any replica. So, the reference signal is lost to the receiver. So, receiver will not be able to make out what to do with the received signal, and it won't be able to extract the range, velocity, etc. So, that is the first part you should remember, that you require a high power, high frequency pulse modulator for this. Now, previously also we mentioned that a pulse radar can distinguish between moving target and a stationary target. Now, here we will say that a stationary target, its return that comes to the radar, that is called by a term called clutter. So, this is an important term, that what is clutter. So, here I am defining clutter as echo of a stationary object. Now, generally we are not bothered with this stationary object, because actually the pulse radar's job is to detect a moving target. So, this is clutter and it is an unwanted thing. So, we need to, but sometimes the clutter is much high and the actually target's echo that is buried in the clutter. Suppose a aircraft is flying near the hill is in the backdrop of the aircraft. The radar is looking, this is the radar, it is looking at an aircraft. The aircraft is coming here, and suppose there is a large hill here. So, this hill's return sometimes maybe 60-70 dB higher than the return from this scatter from this aircraft. So, clutter removing is a very serious job, and actually pulse radar get it inherently. We will see that pulse radar can easily detect, but it requires some extra circuitry, one filter it require, actually that is this Doppler filter, or sometimes it will be called MTI filter, etc. So, that will do the job, because this, if I see the Doppler, actually it does not have any Doppler. So, it can be easily detected that okay, this is a clutter. Okay. And now, the second question that I want to ask is, you see this thing, I also said this question earlier, that it is not coming now. That suppose the a pulse radar can furnish information about the target motion, because it is measuring range. We know the moment we are putting a pulse, we have the waveform has a timing mark. So, I can easily measure range, and with time if we measure range, that means if I measure r as a function of time, then from this thing if I differentiate this, because I have the timing information. So, if I know r t, I can find velocity. So, from the range measurement and with the doing that range measurement with time continuous or with some discrete intervals, I can find the velocity of the target, but that is not done, because there are two reasons. That one is that the velocity of the target, if I have a Doppler measurement, then target velocity is measured explicitly. But as I said that nowadays signal processing is there, so I can implicitly could have done that. But this part B is more important, that this thing actually will not be able to remove the clutter, whether if I do the Doppler measurement. So, Doppler actually separates moving target from clutter. So, this is the most important part, that is why all pulse radar they have a Doppler measurement capability. Now, with this capability, this separating this moving target from clutter or indicating which one is moving target, actually there is a name, one class of radar is called MTI radar or MTI capability. So, those radars who have this MTI capability are called MTI radar. So, MTI stands for moving target indicator, moving target indicator, MTI. Now, actually pulse radar broadly has two classes. One class is called MTI radar, another class is called pulsed Doppler radar. Now, so I can say that pulse radar has broadly these two classes, MTI radar or pulse Doppler radar. Now, you should know the difference. There is a subtle difference between these two. Actually, MTI radar, when we will see it will become clear, but note down that MTI radar, it has a, you see any pulse radar with this MTI facility, they will have both the range measurement and the velocity measurement capability. Velocity is, the range is measured from time measurement, transit time measurement, and the velocity of the target is measured by measuring the Doppler shift produced in the echo signal compared to the transmitted signal. Now, both of these measurement, now we have seen that the range measurement, that can be ambiguity in the measurement, ambiguous range, unambiguous range, this concept we have seen. Similarly, we will just see next there can be also ambiguity in the Doppler measurement, that we will see, that is called blind speed. So, some speed radar cannot see, those are called Doppler's blind speeds. So, there is ambiguity in the Doppler measurement also. Now, MTI radar is designed so that your range measurement is unambiguous. And it's the velocity measurement may be ambiguous. So, what is mean that it is giving very precise thing for range measurement, it is more interested in range measurement, that is why it is making that unambiguous. Velocity measurement it is doing, but it knows that it is not so much important, so it is ambiguous. Whereas, pulse Doppler is the opposite, it is very much required, it is not so much interested in the range measurement. It more importantly it wants to measure unambiguously the velocity. So, I can say that pulse Doppler, for pulse Doppler the velocity measurement is unambiguous, whereas its range measurement may have ambiguity. So, from this actually their application is also indicated, that actually you see that for a, if you have a high speed target, then pulse Doppler is used, because high speed targets are dangerous because you do not have much response time to tackle them. So, their velocity measurement needs to be done very precisely and you will have to take action, whereas for low speed targets we require MTI radar. Okay. So, these are a very subtle difference between them. Now, we will come to a typical pulse radar block diagram and we will understand that. Actually, pulse radar, this diagram with this pulse Doppler radar, it is almost a new thing, mainly in AWACS etc., where you are measuring, the radar is not grounded, radar is in a flying aircraft or flying satellite etc. There this block diagram is not applicable, that is a modern advancement of radar, but generally the MTI radar, that type of radar, this block diagram will be useful. So, let us see. So, now we know that obviously we will have to have a pulse modulator. So, we will see that pulse radar, the pulse modulator in the transmitter portion of the radar. So, we require a, generally radar people call it pulsar. Actually, I will say that you should know it is nothing but our that so called pulse modulator, what we discussed in the simplified diagram. So, this pulse modulator, now the problem is that we will have RF oscillators, and you know that RF oscillators which were used in the early pulse radar, they were mainly magnetron based and they were not very stable in phase, but you see to measure the frequency, actually frequency, phase, these are almost similar type of things. So, if the phase is not stable, when you will give the reference to the receiver, then there will be error in the measurement. That is why you require a very stable phase RF signal. So, magnetron was used because it gives you high power. In early days it was the thing, later klystron was there, but still if you want to have a very precise measurement, you need to make that stable. So, to make that stable, actually two oscillators are used in this circuit. So, I will draw the diagram, later we will explain. First, there is an RF oscillator, and usually earlier people call it coho. It could have been made by magnetron or klystron etc., which are microwave tubes. You require radar is, these pulse radars are high power. So, you cannot have other type of semiconductor based way, though with the advent of the semiconductor technology maybe one day we will get that, but till still people use this type of magnetron, klystron or TWT etc. Now, this is called coho. Coho means coherent oscillator. We will discuss what is the part of coho, and let us say it is producing a RF frequency of FC, RF wave with carrier frequency FC. Now, this is given, this signal is, this FC signal is not transmitted directly or not given to the pulsar directly. There is a locking mixer, basically a mixer, RF mixer, locking mixer there. So, mixer requires two inputs. So, one of that is FC, and there is also another oscillator. It is not so RF level, it is called stallo. So, it is a local oscillator, stable local oscillator, and that frequency let us call FL. So, it is given to them, and what the A gives, this mixer is producing the sum of these two, FC plus FL, and that is given to the pulse modulator. So, and pulse modulator is fired by a trigger generator. This trigger actually gives the on and off time. So, basically this is the determines the PRF etc. And so, trigger generator actually influences the pulse modulator, this thing. Now, after this pulse modulator, I have an RF pulse. If required, there can be a power amplifier. Or if actually sometimes the whole pulse modulator block diagram, inside there is a RF power amplifier, that is okay. That is given to a duplexer. As we have seen, we require duplexer, and then that duplexer gives it to an antenna. Okay. So, this is the transmitted part. Now, what is the job of this stallo? You see that this RF oscillator, it may not be so stable, but what happens, this stallo is giving it, and mixer so makes it stable, and now this whatever FC plus FL is given at every pulse, it is now coherent with the transmitted pulse. So, I have a reference, actually that reference is put here. So, I will use blue color for these references. There are two references that will go here, and also you will see that this trigger generator, whatever it is giving to the pulsar, it is also, the trigger is also given to the locking mixer. So, locking mixer knows when to lock the phase. So, whatever RF oscillator is giving the phase, now that phase is brought down to a standard value. So, even if the RF oscillator is not so stable in phase, but at every pulse on time, the phase is brought to a standard value by this locking mixer. So, now we have a coherent, that is why it is called a coherence oscillator, though actually it may not be a coherent oscillator on its own, but with this circuitry the transmitted signal always is of a known phase, and that phase reference we will see will be given to the receiver side, will be used. Also this trigger generator, you see it is making the pulse, it is giving its signal to the pulse modulator, also it is giving the thing locking mixer to lock the phase of the RF oscillator. So, now we have a stable locked in phase RF pulse, that pulse is transmitted by the antenna. Now, let us see what happens to the receiver. So, I can say what will be the transmitted frequency. So, let me write that this FC plus FL with a pulse thing. So, I have a I can say an pulse, and there I have this thing. So, this signal frequency is FL plus FC, and its phase is also known, very known stable phase. Okay. This is sent. So, there is target, target will produce the signal that will give me a Doppler shift. So, this duplexer on its return path, it will give me what is the signal FC plus FL plus minus FD, depending on the closing target or the receiving target. That is put to a mixer, RF mixer. Now, this RF mixer is fed by this reference FL. So, its output will be FC plus minus plus minus FD. And this, now this is a very weak RF signal. So, this signal is again put to a IF amplifier. Now, this IF amplifier, it put to a phase, but still we have FC. So, we will have to remove FC. So, that removal, that this FC frequency is coming here, that reference is put to that. So, this is a phase detector. Again, in CW radar we have seen what is a phase detector, basically again a mixer sort of thing with some additional circuitry. So, now the output that is coming, that will be the FD Doppler. So, that Doppler will be measured, but while measuring you see that we will have to remove the clutter, etc. So, that is why this is a MTI filter. What is an MTI filter? We will see next. So, from this I get the MTI output. Okay. So, this is the typical block diagram of a pulsed radar. I should say basically MTI filter type of pulse radar. Pulse Doppler is a different thing. So, I can briefly summarize what I have said, that in any pulse radar the transmitter is turned on and off by the modulator at a fixed rate and for a fixed duration. If oscillator is magnetron, the phase of the RF signal at the start of a pulse may be anything from 0 to 360 degree, but we know that in an MTI the phase of the return deco must be compared with the phase of a reference signal. So, echoes from fixed targets will have fixed phase difference from the reference, and moving targets produce echoes with continuously changing phase at the Doppler frequency. So, it is necessary that the reference signal be locked in phase with the transmitted signal, so that these two signals are coherent. The radar is called coherent MTI radar. So, despite the RF oscillator phase being random, the reference signal is coherent with transmission. This is the, that is why it is called coherent MTI. Now, duplexer, it multiplexes the transmitted signal and the received signal. I should actually draw it both ways, so that the duplexer is sending, so that two arrows should be there. So, usually this duplexer may be a circulator, may be some tear tube, modern day tear tube technology has improved. So, you can have a tear tube. Now, RF oscillator usually magnetron, but presently the power amplifier is inbuilt with this, and so it is Klystron or TWT, etc. Now, so what will be the actually the IF amplifier that I put, actually that is, I prefer to call it receiving amplifier, and usually it is a matched filter, which is the most appropriate filter for very low noise signal, and to maximize the noise. If you know the RF signal that has been transmitted, that signal shape, then it is matched to that. Usually it is a match filter. Match filter. We will see match filter in details in the detection theory. Also in communication you have seen that. So, it is that, and the phase detector, what it is detecting, you see it is having the received signal phase, it is having the transmitted signal phase. So, that it compares. So, if we now plot that, actually with time what you get. So, if I plot time versus phase detector output, you will see something like this. The phase, but you will also see that there are in some places then like this, and now how the MTI filter output will look. What MTI filter does we will see later, but finally what we will say, these are all from stationary target, and moving targets, you see the moving target phase is continuously changing, whereas the fixed targets, their phase does not change. So, for all pulses the phase of the stationary targets do not change, but moving target its phase is changing. So, you see this is the moving target, these are all clutters. So, MTI output will look something like this, that only here it will give you an indication of that there is a target. This is actually various pulses, with time you are seeing various pulse things are superimposed. So, you will see that this thing will be there, you will be able to understand that this is a moving target. Now, generally the signals are bipolar, because phase can be in both ways. So, that is why generally if you put it to an average voltage indicator, it will be 0. So, generally this bipolar signal MTI filter output, that is given to a rectifier and you given to the display shows that there is a target. So, let us just briefly write that, let us say the RF oscillator, that its signal, if I call it sine 2 pi f1 t plus some random phi. Now, after the reference, so from that the coho makes the reference signal. So, reference signal will throw away, and let me say that the standard phase it makes at a start of every pulse is 0. So, it will be something like this. Now, at the output of the match filter or IF amplifier output, same IF amplifier or match filter output, it will be something like A1 sine 2 pi f1 plus minus fd into t minus 4 pi f1. This we have seen that if you a target is at a range of r naught, then the phase it gets is this. Now, after mixing, so that means I have this standard reference signal and this. So, the phase detector after mixing, I can say the phase detector output detector output can be written as some, or I can V reference 1, it can be made A2, it can be made A3 sin 2 pi f d t minus 4 pi f1 r naught by c. So, that actually we have plotted in the previous one. Now, for stationary target, this is not a function of time. So, I can say that if this signal I called, or I can say that this output let me call V difference. So, for stationary target, V difference is not a function of time, and for moving target, V difference is a function of time. Now, what the MTI filter does, so that we can separate the clutter, that we will discuss in the next class. We will see various MTI filter designs, because that is new that you do not know. So, that we will see in the next class. Thank you.